And just five. I'm a lab, but from five. Name of perspective. I'm a lab. So just like three classes. What's it called? Yeah. Well, it was I don't know. I think it was the homie. It was the homie that. One with the app. Oh, I'm from the last lab. This is you with him. What? It was a second scary one that. For the boy. I'll just show you. Oh, oh, that's OG. But I think he has scholars. Okay, I'm just well, for my class, do you have saying for enough? Or not? I think this who do I have? I'm just supposed to be deciding. That's what I mean. Pretty sure, yeah. Pretty sure we have. Are you seeing it? Just that. So there's two stations. That one's maybe. Hopefully I get the station. Wait, no, how long was it? It's so cool. I'm in the lab. Always sitting out there, never sitting. What doesn't need a sorry? Or just pretend so. Why would they get no, they get over the good thing when I've been done and no, I went to the name. That was the first one. See, yeah, the guy unique. Hey. You might got around you find a different one. They. This is more. No, you're good. It's really interesting. I don't think Troy would be told.
Without question, yeah. So, for my graduate, I went into my graduation status this morning. Yeah. And I applied back in like October. I'm still in the department. Yeah, we're working on it. Okay. Yeah. So first 2 weeks is a little bit hard for us to get to it just because things are a little bit hectic. But we're gonna get to it weeks 3, 4, 5, and 6. Gotcha. You'll be good to go before. So. Okay. Cool. Yeah. Yeah. Because I want to double check this. Like I said, like 2 months now. Yeah. So the way it's administratively. We didn't pull it until January. So, gotcha. Yeah, so the system only lets us pull. You're in the system. We're gonna do it probably next couple of months. Okay, perfect. Thank you. Thank you. Didn't meet you, but it was oh, but I still mentioned. Yeah, next year. You will walk in with yeah, and Joe always looked at the happy us. Both of y'all, y'all just like, yeah, like morning. You guys were just pulled up. You come back from you're gonna be doing anything like that. Hey, Al, how's it going?
Like currently or just? I do. I actually just need a bus. Yeah. I gave. Oh, you did?
No, I don't. No.
But yeah.
I have
a lot of fries.
Oh, really? I have cats though, so I think they'll want to try to eat them. Yeah. That's a little bit too traumatic. I don't want to be responsible for fish.
No, but I have way too much right now. I have to, I would tag for them.
Oh, really?
Yeah.
Wow.
Be like, hey, what's up? My name is this. Like, when you guys working on, like,
Dang.
you know, I curious to know more about.
And I bought them like during our last semester.
Yeah.
It's like 2 or 3 months with nothing.
Yeah.
And then during the winter, of like 3 weeks, it was like,
Oh, wow.
this crazy. It's like 15 or 20 plus.
Wow. That's crazy.
Hi, boy.
Oh, thanks.
I was wondering.
Good.
Go talk to everybody. Go talk to us.
I was gonna say something, like, maybe focus on the late.
For me.
I realized I was part yesterday, so. Good job, you made serious. I don't do anything, I'm on the team in name only.
Because we're the same semesters, figuring
No,
out.
I mean, like, that's how you.
But it's good, it's not everybody, so we can.
Do that. I can't tell them to speak to the team, like, you're like.
I mean, he does a lot.
Oh, but
He's been slacking for the past couple of weeks.
Oh.
He's getting back into the grind, back.
Right now,
Your version of slacking is, hey, we're gonna change our prompts. And then in 2 days later, hey, can you fill out the post for the next shot? Like, dude, I just found out. Actually,
How was your weekend, Dr.
Can you learn how to disassemble and reassemble bots? You have 1 week. Yeah. Hey, I just want you to machine your own pistons and go inside.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. Having a good first weekend. Has it sunk in yet that the spring semester has begun yet?
So.
Yeah, I know. Same here. Looks like one weekend. All right, but today we have a full schedule today. Well, we have a full schedule every day. So we're going to be continuing where we left off. So I think we left off in the middle of an example last time. So we'll pick up right there today. So we'll finish that up. We'll finish talking about the heat equation, and then we'll finish up today talking about the idea of thermal resistances. So, you know, we're basically going over 2 different ways to solve relatively the same problem. So, you know, I think it'll be nice to see them both side by side, right? Okay, so some announcements before we begin. Homework 1, that is out there for you guys. Homework one is due not this Thursday, but next Thursday. So you guys still have a bit of time. But I think after today, you should, it should start to make a lot more sense, especially the heat equation problem, which is the problem 2. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. Let's go ahead and get started. So let me go ahead and take us back last week. Oh, I'm in the wrong class. That was 308. Okay. So last week we were looking at this problem right here. Okay. So if you remember, near the end of class last time, we just finished our first example using the heat equation, and this is the kind of example number 2. So this is a little bit of a step up. So there's a little bit more going on here compared to our first one, but I think it'll give you kind of a good practice in both in using the heat equation. Okay. So if you recall from last time, the heat equation is basically a differential equation that lets us solve for what I call the temperature distribution in a solid. Okay. So basically, we have our solid right here, and we want to find out, what's the temperature at different locations within this solid. Okay. Because what we're going to get from the end of this is we're going to get a function t of x that's going to tell us how the temperature is distributed. Okay. So that's the goal. And so in this problem right here, we have a situation, we have a wall, okay? And we have numbers this time, which is, what we didn't have last time. So we have the length of the wall is 50 millimeters. So I don't have included here, so let me go ahead and draw that in. So the thickness of this wall is 50 millimeters. We know the thermal conductivity. Thermal conductivity is 5 watts per meter degrees Celsius, okay? One side of the wall is exposed to convection. So on the left side of the wall here, we have a moving fluid that's pushing past the wall. Okay. The temperature of that fluid is 20 degrees Celsius. And the right side of the wall is insulated. Okay. Now, I mentioned it briefly last time, but insulated, all that really means is that there's no heat transfer that can occur past that wall. Okay. It's very much the same thing as, what you would consider like an insulated insulated like an oven mitt, right? So the reason you use oven mitts is that oven mitts are made of a material that makes it very difficult for heat to pass through them. Okay. Okay. Another thing that we know is that we know the surface temperature on the outside of the wall here. So this TS right here, this is 120 degrees Celsius. Okay. Right. And we actually want to compute a couple things in this problem here. So, here's our setup. So one thing that we want to compute that we mentioned last time is that we want to compute the magnitude of thermal production that's going on in this wall. Okay. Because this wall is special. It's actually able to produce heat. Okay. But along the way, we're also going to be solving the heat equation. So we also want to solve for the temperature distribution. T of x. Okay. We're just going to solve. We're going to be solving the heat equation, so we're going to get a solution for T of x just as a byproduct of that. Okay. Okay. So this is very similar to the last example that we did. It's just that there's kind of some more stuff going on. Okay. Okay. Bless you. So whenever you have a problem here that's asking you to solve for the temperature distribution or T of x, what that tells you that this is a heat equation type problem. Okay. Okay. And so the heat equation problems, they always start by writing out the heat equation. So let's write out the full heat equation. Okay. So you have partial squared T, partial x squared plus q dot over k is equal to 1 over alpha partial big T over partial little t. Okay. Okay, so I would recommend, whenever you have a heat equation type problem, start with this. I know, in every single problem, we're going to be canceling terms based on our assumptions. But it's always good to start here just so that you kind of know what you're doing. Okay. All right. So our heat equation here, right now we can't solve it because it is a partial differential equation. So the next step is to cancel some terms. Based on our assumptions. Okay. So let's list out some assumptions for this problem. So for this problem and for basically every problem that we're going to be doing, the first assumption that we're going to make is that we have a steady state problem. Right. So first thing we're going to do is that any derivative with respect to time, we're going to cancel that out. Okay? So any partial derivative with respect to time equals to 0. Okay. So you can see we have one term like that. And so the entire right-hand side here where we have partial derivative of the temperature with respect to time. From the steady state assumption, we can go ahead and cancel that out. Okay. And then as a consequence of this, we can then take our spatial derivative. Okay. And we can transform it into a regular derivative. This is mostly a superficial change, but it is true because now our temperature is only a function of x. And so since it's only a function of one variable, we can change the partial derivative to a regular derivative. But, again, this is mostly superficial. Okay. Doesn't really change the way you solve it. You're still going to be integrating it, but it's good to kind of change. Okay. Okay. Now, if you look back at our last example problem, another assumption that we made was that we said that there was no thermal production. Okay. Okay. That's normally going to be the case in 95% of cases because most materials that you're going to be normally working with as an engineer are going to be what I call inert materials, and so they're not going to be capable of producing any kind of thermal energy. Okay. So I'll say this is true 90, even higher than that, maybe 97.333 repeating, of course, percent of the time. Okay. So thermal production is not a common occurrence. Okay. It turns out in this, so when you can cancel out thermal production, remember, is the second term in this equation, so the Q dot over K. Okay. So normally we're going to cancel that term out as well. But this problem belongs to the 1.6777 repeating, of course, percent of the time where we actually do have thermal production. Okay. So in this case, we're not going to cancel out, but I just want to remind you that most of the time you are going to cancel out that Q dot term, just this time you're not. Questions?
A reminder of what the representation of alpha is.
Oh yeah. Oh, actually, yeah. So we didn't actually cover that last time. So alpha right here is a parameter known as a thermal diffusivity. I kind of skipped over it last time just because, right now it's mostly not relevant because we're doing steady state stuff. We're going to come back to thermal diffusivity, I think, in week 4 or 5, depending on our pace, when we do kind of transient conduction. But so we'll come back to that. If in a nutshell, that thermal diffusivity is a term that tells you how quickly your material can absorb heat and store heat. Okay. So it's almost like thermal capacity. So, but it's combined with a couple other things like density and thermal conductivity there as well. Okay. But for now, it's mostly not relevant, so I kind of skipped it. Okay, and so since we're going to keep the thermal production term here, let me go ahead and rewrite our heat equation. Okay. And so for this particular problem, our heat equation is like this. Okay. The good news for us is that the thermal production or the thermal production and the thermal diffusivity or thermal conductivity, excuse me, both of these are constants. So neither of these terms depend on X. So what we can do is then we can then subtract this from both sides. So we're basically going to move this term over to the other side of the equal sign. And so we have d squared t dx squared is equal to minus q dot over k. Okay. And since that term there is a constant, what we can do now is we can integrate. Okay. And we can just integrate this straight up, which is quite nice. Okay. So we integrate this with respect to x. On the left-hand side, that integration is going to cancel out with one of the derivatives, and so we just end up with dt dx. Okay. On the right-hand side, we integrate q dot over k, which is a constant. So you have minus q dot over k times x. We have to add our c1, okay, because we're doing an indefinite integral. And then to complete the problem, let's integrate one more time. Okay. We integrate one more time, we get t of x is equal to, we have integral of minus q dot over kx, which is minus q dot over 2k x squared plus c1x plus c2. All right, and then once again, we arrive at this point. We have a solution to the heat equation, but it's only a general solution because it's only specific up to a few arbitrary constants. Okay, so C1, C2 right now are still unknown. And technically, we have one more unknown in this problem because we don't have the thermal production term as well. So right now in our solution, we have three unknown values. Okay, so Q dot C1, C2. Okay. All right, any questions up to this point in the problem? Okay, good. Okay, so we need to find values for these three quantities. Okay, and so just like we did in the first problem, the way we're going to solve for these quantities here is we're going to apply boundary conditions. Okay. So we need to apply conditions based on the problem statement in order to solve for their values. Okay. Okay, and since we have three unknown values here, we need to actually apply three boundary conditions. We're going to do this 3 times. Okay. So this problem actually introduces us to a couple new types of boundary conditions because the last problem that we had, we only worked with one type of boundary condition, which was a specified temperature. Okay. This problem actually introduced to us, a few other ones. Okay. Let me go ahead and highlight them for you here. Okay, so I've scrolled back up here. We're looking at the problem again. Okay. So first boundary condition, let me start with the simplest one. Let's start with this one right here, okay? So this boundary condition is basically telling us that we have a thermometer that's right on the outside surface of the solid, and that thermometer is telling us that the surface of this material is 120 degrees C. Okay? So this is what's called a specified temperature boundary condition. Okay. Which is exactly the type of boundary condition we did in the last example. Right? Okay. So let me do this too, since we need to establish a coordinate system here too. Let me call the left side of this solid, we'll call that x is equal to 0. And then the right side of this wall, the one that's insulated, we'll call that x is equal to L. Okay. We need to know the locations of these boundary conditions in order to apply them. Okay. So let's start with the specified temperature boundary condition. So let's come down here. Okay. So let's go specified temperature. Okay. So a specified temperature boundary condition is probably the easiest to work with, because basically what we could say is that, we will enforce the temperature will be a certain value at a certain value of x. Okay. So for this problem, our specified temperature boundary condition states that T at x is equal to 0 is equal to 120 degrees C. Okay. Yeah, question.
Not at steady state, can this assumption be made?
No, that's a good question. So if we're not at steady state, then the surface temperatures could be changing. And so that's something that we would take into account as well. Yeah. Mm-hmm. Yeah, it all depends on the problem and kind of what you're given. Mm-hmm. Okay, so let's go ahead and apply this boundary condition. So to apply this boundary condition, we're going to take our general solution, okay? And we're going to plug in the specified value of x, okay? So we're going to take our general solution, plug in x is equal to 0. So we have minus q dot over 2k. Normally it's multiplied by x squared, but we're going to plug in x is equal to 0. So that becomes 0 squared plus c1 times 0 plus C2, okay? That whole expression there is going to be equal to 120 degrees, okay? All right, and so of course, everything here that's multiplied by 0, we're just going to cancel that out. Okay, so 0 squared is 0, C1 times 0 is 0. And so all we're left with here is 120 degrees is equal to C2. And that gives us the exact solution for C2. Okay. So that one's pretty straightforward. So specified temperature, I think probably the easiest type to work with. Probably the most common too, just because thermometers are a thing and you can measure temperature on a surface pretty easily. Okay, so now let's get to the other boundary conditions, so the next two boundary conditions are going to be new. So let me scroll back up to the problem statement up here. Okay. So next boundary condition, let me use purple for that one. Okay. So next boundary condition, let's do this one. Okay. And so whenever a problem tells you that, you have an insulated surface or there's some kind of insulation, that's another type of boundary condition. Okay. So this type of boundary condition is one that we call a specified either heat transfer rate or heat flux. I'll just call it specified heat transfer. Okay. Right. So insulation, is a special case of this. Insulation just means that the specified heat transfer is 0, but it's possible to have a non-zero specified heat transfer. In fact, one of your homework problems has this as well. Okay, so let's come back down here. Okay, so the second type of boundary condition that you can have on heat transfer problems is a specified heat transfer. Okay. And so in these types of boundary conditions, we are going to basically enforce that a certain amount of heat is going to pass through that surface. Okay. And so how do we formulate this mathematically? Well, let's go back to the very first equation that we went over last Thursday. Okay. So we do have an equation that specifies heat transfer through a surface, and that's Fourier's law. Okay. So Fourier's law, remember, is Q is equal to minus K dt dx. We're going to use Fourier's law in this case in this problem. Because we actually have everything that we need to plug into this equation. So let's work on the right-hand side first. Okay. First, we have minus K. Thermal conductivity most of the time is going to be given to you. So that you can consider that a constant. Okay. And then this quantity right here, we talked a bit about this last time. Remember, this quantity, this dt dx, is known as the temperature gradient. Okay. And so I think, last Thursday it was a little bit kind of mystical, a little bit. I told you we talked about how to get that. Well, we actually have everything that we need to compute this, because this dt dx is nothing more than just the derivative of the temperature distribution. And we have that right here, right? Okay, so we're going to take d dx of our temperature distribution. So our temperature distribution is minus q dot over k x squared plus c1x plus c2. Okay. I know we already solved for c2, but I'm just leaving it here. It's gonna cancel out with the derivative anyway. Okay. Okay. So let's go ahead and evaluate this derivative. So we have minus k. Okay. We're going to take that x derivative and apply it to every term in here. Oh, I'm sorry, we need a minus question from the chat. So is the heat equation the same as the temperature gradient then? So the heat equation is actually the second derivative of temperature, right? So we come back up to the heat equation here, we have a second order derivative. So the temperature gradient, you actually get it part way. So actually, if you're kind of clever, halfway through solving the heat equation, you actually do get the temperature gradient there. And so, you can just kind of plug that in from there. And I did forget a 2 here. So there should be a 2 on the bottom there. Question, yes.
I don't know if I noted it wrong, but is there an area missing or no?
Yeah, actually there is. So Fourier's law normally does have an area here. Thank you for catching that. But there is a different form of Fourier's law where you can actually divide the area by both sides. And so this quantity is actually Q over A. So thank you for catching that. Yeah. But this Q over A actually is a certain quantity as well, which is called the heat flux. Yeah. I know there's a bunch of terminology, so I'm trying to keep things square, but I end up kind of being a little bit of a mess. But whenever you have Q over A, that's a quantity known as heat flux, which is the heat transfer rate per unit area. And so the units for heat flux is watts per meter squared. Okay. Sometimes you'll see heat flux, sometimes you'll see heat transfer rate, it kind of depends on the problem. But something good to be aware of. Okay. Typically, actually, heat flux is given the symbol Q with two quotation marks. So that's usually the symbol for heat flux. But a lot of times, in this class, you'll see me use heat transfer rate, heat flux, kind of interchangeably, but just know that there's a slight difference in the units. Okay. Okay.
That's omega over m squared, right?
That's W for watts. Yeah.
Oh,
Okay, so let's go ahead and apply this derivative here. So we have a minus Q dot over K times X plus C1. Okay. So that's what we obtained by just taking the derivative of our temperature solution. Okay. And then what we're going to do from here is we need to set this equal to a specified value for heat flux. Okay. All right. So the heat flux in this case is actually 0. Because remember, our surface at that location is an insulated surface. So when a surface is insulated, okay. So whenever you have an insulated surface, the heat transfer or heat flux through that surface is going to be 0. Okay. All right. Last thing we need to do, so this equation here, we can't solve just yet, just because we have 2 unknowns, but we can at least plug in for X. Okay. And so last thing I'll do here is, this value of X here, let's plug in X is equal to L. Okay. Because the insulated surface is at X is equal to L. Okay. All right, so that was a lot. So let me go ahead and kind of write this as kind of one clean equation here. Okay. So let me just simplify just for sanity's sake. Okay. So doing all that stuff, we have 0 is equal to, I'm going to take this minus K and distribute it through the entire equation. So we have Q dot times L. Okay. Because that minus K up top is going to cancel out with the minus K on the bottom for that first term, minus K times C1. Okay. All right, any questions on how we got this this result here? Okay, good. But the upshot for this is, whenever you have a specified heat transfer boundary condition, remember to apply that boundary condition, you need Fourier's law. Okay. Okay. Now let's go to the last boundary condition, because right now we can't solve this equation because right now Q dot is an unknown and C1 is an unknown. Okay. So we have 2 unknowns. And so we need one more equation in order to solve this. Okay. Okay, so let's come back up to the problem. And let's introduce the last type of boundary condition that you can have on a heat equation type problem. Okay. All right. So the last type of boundary condition is probably the longest to work with.
but it's also quite common. Okay. And so the last boundary condition that we have here has to do with the fact that we have a moving fluid that's moving past the surface. Okay. And so whenever you have a moving fluid moving past the surface, what's going to happen is that you're going to have either heat, most of the time it's going to be heat loss, but sometimes it can be heat gain as well. But you're going to have heat loss due to convection. Okay? And so this gives rise to our third type of boundary condition, which we can have in our heat equation problems, which it's called the convection boundary condition. Okay. Okay. So let me come down here and kind of define what that means and mathematically how we actually work with it. Okay. So in a convection boundary condition, what's happening is that we have heat transfer from a solid to a moving fluid. Okay. And so when you have convection, we have to kind of treat it a little bit carefully. Okay. So actually, convection, Fourier's law actually does play a role here. Okay. Actually, let me do this. Okay. So whenever you have a convection boundary condition, basically what you're saying is that the amount of heat transfer that's leaving the surface at a certain location has to equal the amount of heat transfer that's being gained through convection. Okay? In other words, we have Q here, our Q double prime from conduction. Okay? This has to be equal to Q double prime by convection. Okay? In parentheses at a specified value X. So essentially, the convection boundary condition is a statement of conservation of energy, which is whatever energy that leaves the surface has to be gained by the fluid. Okay. So let's fill in values for this. And so for Q conduction, I'm going to go ahead and use the heat flux forms. I'm going to divide by A. Okay. We know an expression for this. So we're going to use our good old Fourier's law. Okay. So Q conduction here is going to be minus K dt dx. Okay. And we're going to evaluate this at xb. Okay. We're evaluating that at a certain value of x. Okay. And then for the heat loss due to convection, we're going to use another law of heat transfer, which was come up with by another famous, ancient mathematician. Believe it or not, it's from Isaac Newton. Less known for this than his contributions to classical physics, but this is important all the same. Okay. So the heat transfer due to convection is given by what's called Newton's law of cooling. Okay. And so this equation is given by the following. We have H times T infinity minus T at X is equal to XB. Okay. Okay, so let me go ahead and define a couple of these new terms here. So first we have H. So H, of course, this is our convection coefficient. Okay. So we mentioned convection coefficient very briefly last time, but just to kind of remind you, convection coefficient, this is a basically a property of the flow of the fluid that's moving past the surface. Okay. So this describes kind of in a nutshell, it describes how strong the convection heat transfer is to that fluid. Okay. And that convection coefficient is actually a function of a lot of things. And so if you remember last time, it is a function of the type of fluid that you have. And so certain fluids will have, will make it easier to transfer heat to. But it's also a function of the speed of the flow, the direction of the flow. And so, we can't just say that it's a property of the fluid. It's not something you can look up in a table. And so it's something you have to kind of solve on a case-by-case basis. Okay. For now, for the first, 5 weeks, this is something that's just going to be given to you. But, the whole second part of the class, after the first midterm, we're going to find out how to actually compute this, which, you'll find out is there's actually not that many good methods to doing that, but, you can do our best.
Is this like, is this similar to like the conservation of energy where like heat is conserved when it's transferring from solid to a liquid?
Yep. Yep, that's basically everything here. So basically this is saying that no heat is lost. Basically any heat that's lost from the surface or the solid has to go into the fluid.
Gotcha.
Yeah. Yeah, and then so the other parameter here that's might be a little bit new is T infinity. So T infinity here is the temperature of the fluid.
Why do we call it infinity?
Yeah, so we usually call it T infinity because normally T infinity describes the temperature of some kind of ambient conditions, and so it's the temperature really, really far away. Yeah.
But if you had kind of a closed system, like a certain volume of water or fluid, would it not? You'd call it something else, right?
You can call it something else, yeah. But this equation or the way that this expression was derived was for a very large. Yeah. The reason we use T infinity is that usually for a large body of fluid, the temperature is pretty constant all throughout. But if you have kind of a small space, you could have, a gradient of temperature through the fluid, which you would have to account for too. But then normally if it's, depending on how you compute H, you can account for that here. And then instead of T infinity, you would maybe use like the average temperature of that fluid, but it gets complicated. Convection is very complicated. Yeah. Question.
The gradient can also be really close to a surface, right? And then it's basically just constant. for the
Exactly,
rest of the
exactly,
space.
exactly. So that's
Zoom in a lot. Smaller space,
Mhm.
yeah, the gradient might matter more, but like overall, it's gonna be pretty widespread.
exactly, yeah. So this also accounts for the fact that you could have boundary layers too. And so this is the temperature of the fluid outside the boundary layer. That's kind of the more strict definition. Yeah. All right, any other questions on this expression here? Okay, all right, so let's go ahead and apply it. So we have actually quite a lot to plug in here. So convection boundary conditions are probably the least fun to do because you have to plug in two locations here. And so you have to plug in for the Fourier's law, you have to plug in for the derivative, and you have to plug in on the right-hand side for the surface temperature as well, right? Okay, so let's go ahead and plug in, and let's note. So let me just scroll back up to the problem for a second. The convection boundary condition here is occurring at x is equal to 0. Okay. But that's only for this problem. So remember, for every problem, you have to check and see where your convection boundary condition is occurring. Okay. So let's go ahead and plug in. So first we have the left-hand side, which is Fourier's law. So I'm just going to plug in for that just because we just computed it last time. Okay. So we have minus k multiplied by q dot over k times x plus c1. Okay. This is equal to h multiplied by t infinity minus t at 0. So t at 0, let me put another parentheses here. This is minus q dot over 2k times x squared plus c1x plus c2. Okay. So this right here is dt dx. This right here is t of x. Okay. So let's go ahead and plug in x is equal to 0. So basically everything with x here, we're just going to cancel out. Okay. So that first term there is going to cancel out. This term here is going to cancel out. And that C1x term is going to cancel out as well. Okay. So for this particular problem, it ends up working a little bit conveniently because we have x is equal to 0. Okay. All right. And then we solve this through, we get minus k times C1 is equal to h t infinity minus h C2. Okay. So let me divide both sides by minus k, and that's going to give us an expression for C1. Okay. So for this particular problem, the good thing is that we cancel out everything that has to do with q dot because we've plugged in x equal to 0. So we can solve for C1 outright. Okay. And so C1 in this case is hc2 minus ht infinity, all divided by k. Okay. And if we plug in our values here, we have, let's see what we have. We have H is equal to 500 watts per meter squared degrees C. We know C2 is 120 degrees C. T infinity is 20 degrees C. And K is what? 5 watts per meter degrees C. Okay. Okay, so all those values were given to you in the problem. Okay. And so we plug all those in, and what we get is C1 is equal to 10,000 degrees C per meter. All right, any questions on how we got this this result here? Okay, sure.
For H, what is the C before degrees Celsius again?
That is just me being a derp, so that should just be degrees Celsius.
Okay.
Thanks for catching that. Yeah. That should just be 1 degree there. Okay. So now that we have C1, let's go ahead and plug this back in to solve for Q dot. So if we go back up a bit, we come back up to our boundary condition number 2, we have this expression for Q dot. Okay. So let's take that expression and let's plug in for C1 and solve for Q dot. We're taking our boundary condition 2 and just plugging in for this. Okay. Okay, so our boundary condition 2, what 0 is equal to Q dot times L minus K times C1, I believe it was. My memory, short-term memory is okay. Yep. Okay. So if we solve for Q dot, we get Q dot's equal to C1 times K divided by L. Okay. We have everything here. So we have all the values here. I think the only new one here is L. But just to remind you, L is equal to 50 millimeters. But remember, we have to convert this to, we have to convert it all to the same unit system. So this is 0.05 meters, okay? And so we plug all that in, we get Q dots equal to 1 million watts per meter cubed. All right, and so now that we have our 3 unknowns, we can put it all together. And so let's plug in our 3 constants into our general solution. And let's get our final answer for the temperature distribution. All right, so our temperature distribution T of X is equal to, we have minus Q dot over 2K. And so that is minus, so K is 5 here. We divide, I'll just plug it all in. So we have 1 million. Okay. Divided by 2 times 5, which is 2K, times X squared, plus C1. C1 we know is 100,000 or 10,000. X plus C2, which is 120 degrees C. Okay. We just simplify that first term there, so we're going to end up with a divide by 10. Okay, so that's going to knock off 1 0 here. And so our final temperature distribution here is minus 100,000 X squared plus 10,000 X plus 120. All right, any questions on this example here?
That whole thing is just degrees Celsius.
Yeah, all things degrees Celsius. Mhm. Yeah, so very long example, but we had to talk about the different types of boundary conditions. But, hopefully with this one and then the example we did last Thursday, then you guys should be good on heat equation stuff. Okay, one thing I'll note before we move on to thermal resistances, just to give you a little hint on the homework. Okay, so this is homework 1, problem 2. So homework 1, problem 2 is it is a heat equation type problem. It may not seem like it just from the picture, but it is a heat equation type problem. Okay, I gave you kind of a very interesting kind of situation here. So what I tell you is that I'm giving you what's called a heat sandwich. Okay. Okay. So the geometry looks like this, and so you have basically 2 inert walls, and in the middle, what we have here is it's a very thin electric heater. this thin electric heater, you know the power output of this heater just because you bought it off Amazon or something, okay? So the thin electric heater has a known thermal output. Okay. And so let's call that Q naught double prime. Okay. And so you can see it's given to you in heat flux, okay? And what the problem is asking you is, based on this, and I think there's a fluid moving on the outside too. Okay. Okay, so you have convection on both sides. What this problem is asking you is to find out or solve the temperature distribution within the solid itself here, okay? Okay, so first thing to note is to make use of symmetry. Okay, I think the problem may tell you this, but I'll tell you again. The left and right sides of this are identical, so don't solve for both, just solve for one. Okay, so if you solve for just one side of the problem, you solve for both sides. Okay. Okay, so that's your first hint. So first hint is don't solve both sides, just solve one. Okay. And the other hint I'll give you is, it's a little bit confusing, I think, based on the wording of the problem, but the only place that can actually produce heat is this heater right here, okay? Besides that heater, this material is completely inert. So when you're solving your heat equation, there should be no thermal production, okay? But then how do you account for that thermal heater? If you're going to assume that there's no thermal production? Well, one way that you can account for it is that when you apply the boundary conditions on one side of this problem, okay? So let's say that you're applying your boundary condition on the surface that borders the electric heater, okay? When you apply that boundary condition on that side, you can use boundary condition number 2 for a specified heat flux, okay? Because what do you know? You know that the heater is outputting a certain thermal output, okay? And so everything that thermal heater is going to produce is going to go into the solid, okay? Except instead of like the last example. So in the last example, we set, Q is equal to 0, right? Because it's an insulated surface. Here, it's not going to be equal to 0. So now, the specified heat flux is going to be equal to the thermal output of the heater divided by 2, okay? Why is it divided by 2? Well, because, we have 2 halves here. And so if you're only analyzing 1/2, only half of that heater's output is going to go into that side, okay? Right. So when you're doing this problem, I know the wording of the problem can be a little bit tricky, but there's no, at least in the area that you're solving the problem, there's no thermal production. And just make sure that you account for the heat transfer from the heater as a boundary condition. Okay. But that's a lot of hints, and so hopefully you guys will be able to do that from here. Okay. All right. And so from there, let's go ahead and move on from the heat equation. And let's go ahead and move on to our next topic, which is thermal resistances. Okay. Thermal resistance. So, we just spent the last, I would say lecture and a half talking about the heat equation, right? And traditionally, the heat equation is, the way to solve heat transfer problems. So you solve for the temperature distribution. Once you have the temperature distribution, you can solve for the heat transfer rate, okay? But solving the heat equation, for every thermal situation can be a little bit cumbersome. Because, you have to solve a differential equation, and you have to apply boundary conditions, and then you have to take the derivative. And so, it's not always the most efficient way, especially when you have a relatively simple case, or in some cases you have a relatively specialized case. Okay. In fact, let me kind of give you a situation which would be a pain to solve with the heat equation, which is a situation that happens a lot in practice. Okay. So let's say that you have a layered material. Okay, so each of these layers here represents a different material. So this is material 1, material 2, 3, 4. And so they all have different material properties. Okay, so they all have different thermal conductivities. They all have different lengths. Okay. Right. And so if you wanted to solve a problem like this, and by the way, this is very common. It's very common in thermal design to layer different materials on top of each other to take advantage of their thermal properties. Okay. In fact, one of your homework problems is like this too. So problem 3 is exactly like this. Okay. If you were to solve this problem with the heat equation, you would have to solve the heat equation in every single layer of this material. Okay. So you'd have T1 of X, 2 of X, T3 of X, T4 of X. Okay. So that's 4 times you have to solve a differential equation, 4 times you have to apply boundary conditions twice. Okay. And 4 expressions for the temperature, which, is a pain, especially for something that happens so commonly like this. Okay. And so thermal resistance is a fairly, well, at this point, it's not that new, but relative to the age of the heat equation, it is a new development to make analysis of these types of systems a bit simple. Okay. Okay. So how does it work? And why is it called thermal resistance? If you've taken a circuits course, this actually will be, familiar, hopefully, to you. If you have PTSD from circuits, don't worry, it's not going to be that bad. But it does help to kind of have that intuition. Okay. Because what happens for an electric resistance? Okay. So for an electric resistor, let me go ahead and draw our image here. Okay. So in electric circuits, a resistance we can say has a resistance R. Okay. And if there's a voltage drop across the resistance, and so if there's a voltage V1, a voltage V2, okay. If there's a difference in here, and so let's say V1 is greater than V2, okay. What's going to happen in that situation? So you have a voltage drop across a resistance. That's going to drive current across the resistance, right? And in fact, we actually have an equation for this. Okay. And so the equation that describes the amount of current that goes across a resistor is known as Ohm's law. Okay. So Ohm's law basically says that the voltage drop, or V1 minus V2, is equal to the current on the resistance multiplied by the resistance itself. Okay. V is equal to I. Okay. Probably the first equation you learn in electric circuits, and that's the only equation we're going to use, trust me. Okay. So let's compare the situation to heat transfer. Okay. Because what's the fundamental law of heat transfer? It's not actually the fundamental law. It's just the way I think of heat transfer. Is that heat goes from hot stuff to cold stuff, right? And so if you have an object here, okay, and this object is exposed to a temperature difference, right? So you have T1 on one side, T2 on the other side. And just for the sake of argument, we'll say that T1 is greater than T2, okay? What's going to happen in that case? And so what we know and what we've been talking about for the last two lectures is that when you have a temperature difference between two points and there's a solid connecting them, that's going to drive some heat transfer across that surface. Or in other words, you're going to have a value of Q, okay? And so what if we form kind of a similar Ohm's law here? And so if we say that T1 minus T2, okay? And so instead of a voltage drop, we have a temperature drop instead. Okay? What if we say that T1 minus T2 is equal to the heat transfer rate multiplied by some resistance? And so can we come up with something like an Ohm's law for heat? Okay. And so, of course, the answer is yes. I wouldn't have brought this up otherwise if the answer was no. But the question is, what do we put for this resistance here, right? Because, unlike electric resistors where you can just go to Radio Shack and buy a resistor of a certain value, heat transfer goes through, it's a little bit more complicated for heat transfer, okay? So before we go today, let's come up with an expression for the thermal resistance, and I'll show you a few different applications for this. Okay. So to get an expression for the thermal resistance, let's once again start from Fourier's law. I'm going to use the heat transfer version of this one, so the area is going to be there. So we know Q is equal to minus K times A dt dx. Okay. So that's our classic Fourier's law. Let's plug in for T here. Okay. Okay. Now, you might be saying that, T of X should change with every problem, right? And you're right. So I'm going to plug in a very specific answer for T of X, and that's going to be the T of X when we have a specified temperature on both sides of the solid. Okay. We actually did do this this specific case as an example. So this was the first example that we did last Thursday. All right, and so just to kind of refresh your memory, I'm going to write it in a slightly different form here, just so it's consistent with our expression above. Okay, and so this let's see. So this expression here is given by T of X is equal to, or sorry, should be T2 minus T1 divided by L times X plus T1. Okay. All right, so that was the solution to example 1 last time. It's just I swapped the subscripts for the T just to be consistent. Okay. Okay, so let's go ahead and plug that in here. So we have Q is equal to minus K times A. Okay. We're going to take the derivative of this temperature distribution here, which is pretty straightforward. So that's just going to end up being T2 minus T1 all over L. Okay. Okay. Let me go ahead and simplify this and rearrange the terms. So I'm going to take that negative that's out front. I'm going to distribute it through. So you have a Q is equal to T1 minus T2. Okay. Multiplied by K times A divided by L. Okay. No, just regular Q. So this is heat transfer. This is heat transfer rate, not thermal production. So Q dot is thermal production. Q is just heat transfer rate. All right. And so let me go ahead and rearrange this further. Okay. So I'm going to take this coefficient here, this Ka over L, and I'm going to multiply by its inverse on both sides. Okay. So we have quantity L times K times A multiplied by Q is equal to T1 minus T2. And if we compare this to our Ohm's law, okay, remember our Ohm's law is V1 minus V2 is equal to current times resistance. Okay. Hopefully you see the analogy here, because now what we can say is that this expression in parentheses is basically acting like our resistance to heat transfer. Okay. So this expression right here, and let me actually bring it out here just so to make it a bit more clear, is what's known as our conduction thermal resistance. Bless you.
Bless you.
Okay. So our conduction thermal resistance, so we'll call it R conduction, is equal to L, which is the thickness of the solid divided by its thermal conductivity multiplied by its cross-section area.
This only works for solids.
Yeah. But we're actually going to take this idea in later chapters and kind of extrapolate it to cylindrical systems and spherical systems too. This actually also works for convection, which we'll talk about in a second. All right, any questions on this? Okay, so let's come back up to the situation that we kind of started this discussion with. Okay, so let's say that we have some kind of layered composite material here. Okay, and so instead of solving the heat equation 4 times, what we can do instead is that for each layer here, we can represent each layer with a thermal resistance. Okay, and so let me actually draw it up here. Okay. And so instead, what we can do is we can say this is equal to resistance 1, resistance 2, resistance 3, resistance 4. Okay. Where R1 is equal to L1 over K1 times A. R2 is equal to L2 divided by K2 times A. R3 is equal to L3 divided by K3 times A. And R4 is equal to L4 divided by K4 times A. Okay. And if we wanted to compute the heat transfer throughout this entire system, let's say that we know the temperatures at the endpoint. So let's say we know the temperature out here, T0. And let's say we know the temperature out here, we'll call it TF or T final, okay? And so if we wanted to compute the total heat transfer throughout this whole system, we would just do T0 minus TF, okay? And then what we can do is we can just add up all the thermal resistances that separate T0 and TF, okay? So we have R1 plus R2 plus R3 plus R4. Okay. And so you can solve this problem in just one step as opposed to solving 4 differential equations. Okay. Because what you have is, 4 resistors in series. All right, and so last thing before we go, so there is a thermal resistance for conduction. So we don't have time for an example today, but we'll do an example next time. Okay. But there's also a resistance for convection as well. Okay. Okay. So for convection resistance, let me go ahead and remind you that the formula that governs convection heat transfer is Newton's law of cooling. Okay. So this right here is Newton's law of cooling. Okay. I added an extra A there just because, this is a heat transfer version, okay? But if you want the heat flux version, you just divide by A. Okay? We can come up with the thermal resistance here as well, because, we have all the same ingredients to our recipe from before. So we have heat transfer, we have a temperature difference, and we have everything else. Okay? And so this everything else here becomes the expression for our convection resistance. And so we have resistance for convection is equal to 1 divided by H times A. And so when we come back to class on Thursday, I'll show you how to kind of put this all together and solve what would normally be a very complicated heat transfer problem. But with thermal resistances, it becomes much, much easier. Okay. All right. So thank you guys for coming today. That's all the time we have. So I will see you guys on Thursday for the conclusion for convection notes. But so hope you have a good rest of your day. A question.
Go back up to you're writing. Like up at the start of the problem.
Yeah.
Yeah, all that on the side.
Yeah. Oh, no.
That was a very dungeon. That was like the first dungeon I ever made.
I like this. Quick, like, advice. So I'm telling you about but we planned where I'm gonna do like, I'm gonna have trials in 2 months after this. I'm in my team. But could I like start doing, so I'm only gonna be doing like probably like 8 units each.
Yeah.
My undergrad. Yeah.
Yeah, so what you can do, Dr. Stone asked, you can take extra technical lessons each semester and then count those. Okay, so the way our masters are gonna be, you have to take 10 classes overall. 5 of those classes can be 400 level. You get started.
I'm taking 3 electives right now,
Yeah.
so I would have a fit. I know someone sent me like a petition, so I just fill that out,
Yep.
send it to advising.
Yep.
Right, and then they get signed off.
The most important thing is that your instructor has to know, because he has to give you.
Okay,
But yes,
doesn't matter which one I choose.
not particularly, no. So whichever one you want.
So I have to do 5 upper divs,
Oh.
and how many of those would be 4?
So 10 courses overall.
Okay.
5 of those can be 4.
Okay, gotcha.
The other 5 have-
Man, I should have done that extra, I should have done the extra optimization.
Oh, you could have, yeah.
No, but you would have to take 4 before they let you count it.
Yeah,
Should I read? Oh, I have to do 4.
Before they count it.
Yeah, you can only do that on your 5th technical.
Oh, yeah.
Or it's just for undergrad.
Just like practice early.
There's, I know I'm gonna be, I like registered for graduation, I think and everything, but
Yeah.
there's something about a grad check.
Yeah, we still need to do that, so we're
Okay.
working on it.
So email about that stuff.
You don't have to email, we're,
Oh, you guys are actively
Yeah.
working on it?
yeah, so I think
Okay.
you're graduating summer, right?
Yeah,
Okay.
yeah, I'm summer.
Yeah, we haven't really gotten started on the summer graduates yet, so
Okay.
probably do that next. Probably in like 2 weeks.
Okay, so as long as I like paid the fee and everything,
Yeah.
I'm good for now.
You're good.
Okay,
Yeah,
thank
I
you.
remember seeing your name.
Okay.
For, in my grad program, did I retake optimization?
I don't, actually, maybe, you've got to talk to, Dr. Myrtle, so he is the graduate advisor.
Okay.
So I don't know if you can retake the course for grad, then you do just do the extra assignment.
Yeah.
But
I would
that's a
redo
question.
the final.
Yeah, that's a question for him. Yeah.
Sounds good.
Yeah. Mhm.